backpropagation with softmax cross entropy and the ReLU input-output function for the neurons. Why is it a part of the probability lecture series? The reason is really softmax. And backpropagation with softmax is a kind of modus operandi for deep neural networks. So this is a very fundamental topic. We see this technique in application across neural network architectures, across applications. However, for today, the center stage is held by partial derivatives and chain rule of partial derivatives. So we'll see how application of partial derivatives and the chain rule produces a very powerful mechanism for obtaining the weights of deep neural networks. So I want to quickly go into the mathematics. Today's discussion is based on mathematical derivations and mathematical ideas. But still, to contextualize these rigorous mathematical steps, we need a bit of perspective. I'll quickly give that perspective. We'll come back to this perspective later. But the mathematical treatment is really the thing to pay a lot of attention to. And the mathematics is simple. It's a very systematic mechanical procedure. And it is quite wonderful to see that this systematic mechanical procedure leads to the backpropagation rule of weight change, which is so widely applicable. So now I request again all of you to mute your mics, please. Now, very quick motivation and historical perspective. We see this kind of neural networks, which you see on the screen, very frequently. So there is a scene here, and where the main task is to detect the objects in the scene. So we see that the final softmax layer produces decisions on dog, cat, boat, and bird with the probability values shown against these classes. Dog probability 0.01, cat 0.04, boat 0.94, and bird 0.02. So we see that boat has the winning probability, and indeed in the scene there is a boat. Okay, and the boat is detected because this convolutional neural network has been trained to recognize such objects, not with complete certainty, because there is always noise and ambiguity in the scene also, and therefore the decision is probabilistic. We obtain class decision on the categories based on probability values. Okay, and you can see here fully connected networks. The final output prediction is by means of probability. Before that, we have pooling and convolution. So pooling and convolution is a pair which is repeated many times to pay attention to different features of the image. So this is a very common configuration of deep neural network, be it image processing or speech processing or even language processing. Now, if we look at the history, you should pay attention to the years. Backpropagation came in 1986, and before that in another form in 1972. Then RNN and LSTM came in 1997, and GRU, which is an improvement on LSTM or an alternative to LSTM in a more refined form, came in 2014. Backpropagation came way back in 1980s. Now, RNN really caught the attention because it was so successful in speech recognition. From 2007 onwards, LSTM started revolutionizing the speech recognition problem. In 2014, Baidu used connectionist temporal classification and broke the switchboard hub 500 speech recognition dataset benchmark without using any traditional speech processing method like HMM. So, by the way, things being discussed today, uh, students in deep learning for NLP course, you have seen these ideas, but there is no problem in looking at them again because they're so fundamental. Then RNN was also used for connected handwriting recognition. Connected handwriting is also a kind of sequence processing. Characters flow into each other to form words, then words form sentences. So here again, we need to process sequences of building blocks in corrected handwritten patterns. And here again, RNNs showed very impressive performance and won several competitions in this particular task. Convolutional neural networks came in 1989, but they again got the attention of the world because of the ImageNet dataset benchmark. So millions of images from the web, 1,000 different classes, and people obtained absolutely spectacular results in image recognition and objects recognition in scenes. So the accuracy figures were so much better than anything existing at the time, told people that here is a paradigm shift and new techniques have arrived on the stage, driven by data and machine learning algorithms, which, by the way, were discovered many, many years back. Then RNN applied to natural language processing led to transformer architecture. Look at the years again, 2010 and 2014, where the recurrent neural networks applied to natural language processing. In 2017 came this landmark paper called Attention is All You Need. So transformer architecture was introduced by Bahadanu first of all, but this refinement of Bahadanu's architecture by powerful stacks of attention came in 2017 and was found to be very successful in machine translation. So Google's neural machine translation is based on transformers. This was a paradigm shift from statistical machine translation. Now, limitations of feed-forward neural network, recurrent neural network, convolutional neural networks are also known. Feed-forward neural networks and convolutional neural networks are fixed input techniques. They cannot capture the sequential context. And RNN, LSTM, and GRU suffer from pure sequentiality of processing, and therefore they cannot take advantage of parallel processing. Moreover, they also suffer from the problem of not being able to capture long distance dependency. So if the subject is far away from the verb, then the subject's influence on the verb, like Ram jayega, Sita jayegi, that kind of processing cannot be organized for very long sequences. So now, of course, the latest developments are transformers in the form of GPT-3, GPT-2, and so on. OpenAI, a San Francisco-based AI research laboratory, introduced the third generation of generative pre-trained transformers. And it had 175 billion parameters. So these are really mind-boggling numbers. And before that, Microsoft's Turing NLG had 17 billion parameters. So one can imagine the huge amount of computing power that is needed for training such machines. Okay, But the point is that with all these, developments, important milestones, the perspective, back propagation has remained, I can venture to say, the only technique for um, learning the parameters. Anywhere you look, any technique you look at, it is back propagation, which updates the parameters pre-initialized before the iterative algorithm starts. So backpropagation is really all pervasive for deep neural network learning. Now, the three pillars of deep learning are feed-forward neural network, recurrent neural network. We should also include LSTM and GRU in this, and convolutional neural network. Vishal has a question. I'll handle it a little later. So the three pillars, let us remember, are feed-forward neural network, recurrent neural network, and convolutional neural network. Feed-forward neural networks, which are fully connected, are also called dense networks. What about transformer? Where do they fall in this categorization? In transformer, there is no sequentiality because the positional information is captured. So we can look upon transformer also as feed-forward neural network. And again, the basic learning technique will be backpropagation. Okay, so backpropagation is indeed uh, the foundational idea which is used everywhere. So feed-forward neural network uses backpropagation. Recurrent neural network also uses backpropagation. This is called backpropagation through time because the same network evolves over the whole sequence, looking at all the words or all the tokens one after the other. Now, sometimes a question is asked, are deep neural networks really needed? Is it an artificial um, discussion? How does deep neural network really arise in practice? Okay, it is not easy to spot this in image processing situation, but in NLP, we can immediately see deep neural networks in operation because the RNN, which looks at token after token, if it has to process a sentence of length 30, let's say, then there are 30 stages of recurrent neural network, and each stage is can be looked upon as a set of layers of neural network. So if the original RNN has k layers, then k into sentence length, k into L layers are there in this neural network. So, a deep neural network which is unfolded and which has about 30 layers is absolutely commonplace when we deal with NLP and apply RNN LSTM on this. So deep neural networks uh, are very natural in sentence processing. What about convolutional neural network? Does it use backpropagation? It does. Backpropagation is there at the final stages of processing when there are dense layers, and also in pooling layer and convolution layer. So everywhere you have to change weights, and it is backpropagation which is at work. So a typical dense neural network is a pure feed-forward network where the connections go from layer I to layer I plus 1 in a forward manner. There is no feedback connection. And this is the representative neural network which has been in existence since 60s. A very popular feed-forward neural network is the XOR network because hidden layers were introduced to solve the problem of XOR. We know that a single neuron cannot solve the XOR problem unless it has some very complicated input-output relationship like sine function. So the XOR network is computed by this kind of architecture, where in the hidden layer we can compute x1 bar x2 and x1 x2 bar and OR them or the outputs in the outermost layer. Now, the question is, for such a network, how do we fix the weight values? Okay. So it turns out that we have to give a slightly different treatment for connections going to the outermost layer and connections for the hidden layer. And the difference is also very well understood. In the outermost layer, we have the target values in a supervised learning scenario. And therefore, we know the difference between the target value and the observed value. In the hidden layers, we do not know the target values. So we have to apply some other idea. And this other idea is chaining of partial derivatives. So let me repeat this point. The chaining of partial derivatives is at work when we are training weights by backpropagation. So now the question that arises is when we use backpropagation and estimate the parameters through a loss function, which is cross entropy, and there is softmax at the outermost layer, then fundamentally what are we doing? When we minimize the cross entropy loss on training data, we are equivalently maximizing the likelihood of observation. So this is an important point for us. Minimizing cross entropy loss is equivalent to maximizing the likelihood of observation. Very fundamental observation. And minimizing cross entropy loss is essentially minimizing the distance between the softmax output and the target output that is required. So at this point, it is good to look at the property of softmax. Softmax takes a vector of k real values and converts these k real values into another vector of k real values that sum to 1. The input values can be positive, negative, 0, or greater than 1, but softmax transforms them into values between 0 and 1. So that they are interpreted as. So mathematically speaking, z bar is the input vector to the softmax function, and the ith component of the output coming from softmax is given as e to the power zi divided by summation of e to the power zj, j going from 1 to k, where k is the number of components in the input vector. Zi is the ith component of the input vector. So just one more time, z is the input vector, and the ith component of the input vector is e to the power zi divided by e to the power zj, j going from 1 to k. So to take an example, if z bar is 1, 2, and 3, then z1 is 1, z2 is 2, z3 is 3, e to the power 1 is 2.72, e square is 7.39, e cube is 20.09. So the components of the softmax vector applied on z bar is 0.09, 0.24, 0.67 after we divide e to the power 1, e square, and e cube by the normalizing quantity. So softmax converts a vector into a vector of probability values. So this is a neural network where there is only the output layer and the input layer. And the input values are xi0, xi1 up to xim, where I indicates the ith pattern. The output values are OI1, OI2 up to OIC, where C is the number of classes and I is again the pattern number. So OIC is a softmax applied to the net input vector. So each neuron is receiving a net value which is equal to the weighted sum of the inputs. So net I1, net I2 up to net IC is an input vector which gets converted by Softmax into the output vector OI. Okay, and the cth component is e to the power net IC divided by e to the power net IK, k going from 1 to C, as per the definition of Softmax. So there is no hidden layer yet. Now, maximum likelihood and cross entropy laws, of course, can be understood. We can come back to that later. But what is the interpretation of OIC? So OIC, when you look at this expression here, is the probability of the input belonging to the small cth class. Okay, so OI1 is giving the probability of the input vector belonging to class number 1. OI2, the probability of belonging to class number 2. So if these are dog, cat, boat, and bird, then each of these values give the probability of the input image being that of a dog or cat or boat or bird. Okay, so these are probability values. Now, the likelihood of observation in case of Softmax is expressed in terms of the likelihood as OIK to the power TIK, where T is the target value, O is the observed value. And if we take the product of these quantities over all the patterns and all the classes, so that is the likelihood of the training data. And very simple mathematical operations like taking the log likelihood and taking the negative of log likelihood shows that the negative log likelihood is nothing but the cross entropy between the probability distribution indicated by T and the probability distribution indicated by O. So you can see that the likelihood expression is transformable to cross entropy expression and vice versa by means of simple algebraic operations. So that's why minimizing minus LL is equivalent to maximizing L. Therefore, minimizing cross entropy is equivalent to maximizing likelihood. Now, having looked at Softmax, we need some building blocks, building mathematical blocks. So we are interested in derivative of Softmax. But before that, let's look at the derivative of sigmoid. So from this point onwards, we are going to look at mainly mathematical steps, not much of intuitive description or not even concept description. These are rigorous mathematical steps. So OI equal to 1 by 1 plus e to the power minus net I is the output for the ith input. So if I take log on both sides, then I have ln OI equal to minus ln 1 minus e to the power minus net I. From here, we apply partial derivative, and partial derivative is going to be our main technique, main concept as we go forward now. Take the derivative of the left hand side, 1 by OI into delta OI delta net I. This is the quantity of interest, delta OI delta net I is equal to minus 1 by 1 plus e to the power minus net I into minus of e to the power minus net I. So I am purposefully showing this to you just to tell you that you have been using chaining of partial derivatives all the time. So the derivative, partial derivative of the left hand side is nothing but chain rule in operation. First of all, you apply partial derivative on minus ln 1 plus e to the power minus net I. So ln z becomes 1 by z after derivation. Then I apply partial derivative on 1 plus e to the power minus net I. Partial derivative of 1 is 0. Partial derivative of e to the power minus net I is e to the power minus net I, but the story cannot stop there. You will have to take the partial derivative of net I also, which gives you minus 1, because the derivative is finally with respect to net I. So this quantity is nothing but e to the power minus net I by 1 plus e to the power net I is equal to 1 minus OI. OI is defined as 1 by 1 plus e to the power minus net I. So from this algebra, we come to the conclusion that delta OI delta net I is OI into 1 minus OI. So the derivative of output with respect to input of a sigmoid neuron is output into 1 minus output. A very frequently used result which we'll remember. Now, derivative of softmax. There is a little complication here. The softmax is a function of all the components in the input vector. Okay, so if I am interested in the derivative of the ith component, then the question that naturally arises is that is the derivative with respect to the input to the ith component, ith neuron, or is it with respect to the input to jth neuron, where j is not equal to I? Okay, so that's a very basic point you have to keep in mind. We are taking the output, derivative of the output of ith neuron with respect to the input. Which input? This neuron's own input or another neuron's input. Okay, so this is a small difference from sigmoid neuron, which we need to keep in mind. So when it is with respect to the input of the same neuron, then I apply the idea used in the derivative of sigmoid. So ln OIC is equal to net IC. So ln of E net IC gives me net IC minus ln of this denominator, which is a summation. Now I take the derivative on the left hand side. I get 1 by OIC delta OIC delta net IC. The derivative of net IC with respect to net IC is equal to 1 minus, now chain rule of partial derivatives, 1 by the sum e to the power net IC. All other e to the power net i's will vanish because it is partial derivative with respect to net IC. So this is equal to again 1 minus OIC. So delta OIC delta net IC equal to OIC into 1 minus OIC. So what is the observation? Find here. The derivative of the output of a neuron with respect to its own input is nothing but output of that neuron into 1 minus output of that neuron, just like sigmoid. But we have to finish this derivative story by looking at the derivative of the input of another neuron. So here I again take the derivative with respect to the input of another neuron. So I get 1 by OIC delta OIC delta net IC dashed. So now it is C dashed because I'm taking the input of another neuron. Here net IC does not give me 1 like before, it gives me 0 because net IC is derived with respect to net IC dashed. This gives me 0. Now again, as usual, 1 by the whole quantity into e to the power net IC dashed, and net IC dashed is the input to the other neuron, okay, not the neuron whose output is taken derivative of. So this is nothing but minus OIC dashed. So we make a very interesting observation. Derivative of the output of the neuron with respect to the input of another neuron is minus OIC into OIC dashed. So what does it mean? It means that the derivative of the output of the neuron with respect to the input of another neuron is minus product of output of the neuron in question and the output of the other neuron. Okay, this is quite interesting. So, we come to the conclusion that the derivative of the softmax has two cases. One case is derivative of the output of the neuron with respect to its own input, where the derivative is output into 1 minus output. And derivative of the output of a neuron with respect to the input of another neuron, here we get minus of the product of the outputs of the two neurons. Okay, very useful result to be kept in mind. Now we are ready to jump into backpropagation when softmax is involved. So I'm illustrating this with a neural network which has two hidden layers and one output layer and one input layer. Everywhere the number of neurons is 2. Okay, so this gives me a method of discussing the change in weight process, the process of changing the weights without getting cluttered by lots of notation and many neurons in the network. We can get the essential ideas from a simple network like this. So just to repeat the nature of the architecture, 2 neurons in the outermost layer, 2 neurons in the input layer, 2 hidden layers, and each layer with 2 neurons. And we follow a convention that the number close to the alphabet is the destination neuron, and the number which is separated by comma or is another single number is the index of the source neuron. So W1, 21 is the weight going from hidden layer neuron 21 to first neuron in the output layer. Okay. Similarly, W21, 11 is the weight going from hidden layer neuron H11 in the first layer to the hidden layer neuron H21 in the second layer. So we will be interested in finding out the weight change expressions for a weight going to the outermost layer and for a weight going to the hidden layer. Okay, and we remember it is the softmax function at the outermost layer and cross entropy loss which is being considered, and hidden layer neurons are ReLU neurons. Okay, so can somebody verify that you're looking at a network with 2 hidden layers, 1 output layer and 1 input layer?
Yes, sir.
Okay. So Pranjal Gupta says, can I explain the weight convention again? So the weight convention is as follows. It has a lower suffix, lower right-hand suffix. That lower right-hand suffix has 2 components. Index for the destination neuron, index for the source neuron. Index for the destination neuron is close to the alphabet. Index for the source neuron is away from the alphabet. So W1, 21 means take the first neuron in the outermost layer, and 21 is the first neuron in the hidden layer just below the outermost layer. So 21 is second layer, first neuron, and 1 is output layer number, output neuron number 1. W21, 11 is destination neuron is H21 in the hidden layer and source neuron H11 in the first hidden layer. Okay. So now we have to make use of some results which are applied again and again. First and foremost is the gradient descent rule. We are interested in weight change for W121, the outermost layer connection. So here the delta W121 is proportional to change of error with respect to change in the weight value. Okay, so minus delta E delta W121 is the gradient of error with respect to the weight in question. So change in weight is proportional to negative gradient of the loss function with respect to that weight. This is the basic rule. This is the gradient descent rule. And we have to now introduce a constant of proportionality eta, which is called the learning rate. The learning rate is between 0 and 1. So now the error function or the loss function is minus T2 log O2 minus T1 log O1 for a neural network which has two output neurons. Okay, so the two target values are T1 and T2. Now T1 and T2 are such that they sum to 1. Okay, and each of them are 1 or 0. If T1 is 1, T2 is 0. If T2 is 1, T1 is 0. So this means it is a 2 plus problem. The image can be that of cat or dog. So when cat is true, dog is false. When dog is true, cat is false. Okay, so that's why T1 0, T2 1, T1 1, T2 0. So T1 plus T2 is 1. And since we are getting softmax in the outermost layer, O1 plus E2 also, O2 is equal to 1. And O2 equal to e to the power net 2 divided by e to the power net 2 into e to the power net 1. O1 is e to the power net 1 divided by e to the power net 2 plus e to the power net 1. This is the softmax function. Now come the important results. Because of the fact that T1 plus T2 is equal to 1, O1 plus O2 equal to is equal to 1, this difference of cross products have an interesting form. So T1 O2 minus T2 O1 can be written as T1 into 1 minus O1 minus 1 minus T1 into 1 is equal to T1 minus O1. So difference of cross products is expressed in terms of one of the T's, okay, not both T2 and T1. And T1 O2 minus T2 O1 come out to be T1 equal minus O1, the difference of observed from the target. Similarly, T2 O1 minus T1 O2 is equal to T2 1 minus O2 minus 1 minus T2 into O2. This is equal to T2 minus O2. So this is very nice. The difference of cross products with respect to target and observed is equal to the difference of target and observed. Okay, this is a result which will be used again and again. Another result which is used is the fact that derivative of O2 with respect to net 2 is equal to O2 into 1 minus O2. Derivative of O2 with respect to net 1 is minus O1 into O2. Okay, so these results will be used again and again. Let me just repeat one of the results here, that the difference of cross products is difference of target and observed. Okay? That's an important building block. So now I'll go through the derivation from first principles, which can be can be shortened dramatically if we make use of recursion, which we'll see very soon. Now, we are interested in the change in weight value for delta W1, 21. Okay, here is the picture. We are interested in this weight, which is shown in red, W1, 21. 1 is first neuron in the outermost layer, 21 is the first neuron in the hidden layer below. So apply the gradient descent rule and proceed from first principle systematically. So delta W1 to 1 is minus eta delta E delta W1 to 1. Now, the E does not directly depend on the weight. So we have to express E in terms of its immediately controlling variable, which are W1 and W2. So you see the error value E is minus T2 log O2 minus T1 log O1. So it's a function of the target values and the output values of both the neurons, not a single neuron, but both the neurons. Not only one neuron, but both the neurons. So now delta E delta W, I'll call it W for the sake of brevity. So delta E delta W equal to minus T2 by O2. This is derivative of log into delta O2 delta W minus T1 by O1 delta O1 delta W. Okay, follows from the definition of derivative. Now delta O2 delta W, delta O2 delta W is delta O2 delta net 2 into delta net 2 delta W plus delta O2 delta net 1 into delta net 1 delta W. What is this quantity? Well, O2 is a function of both net 2 and net 1 because of softmax. Okay, if it was sigmoid, then O2 will be a function of only net 2. Because of softmax, O2 is a function of both net 1 and net 2. So the rule of partial derivatives requires me to express the derivative of O2 with respect to the weight through both net 1 and net 2 and adding those quantities. So this is from the theory of partial derivatives. And chain rule is also in operation. So delta O2 delta net 2 into delta net 2 delta W plus delta O2 delta net 1 into delta net 1 delta W. Now comes an interesting observation that the weight of interest W121 feeds into net 1 only, does not feed into net 2. So delta net 2 delta W will be 0. So delta O2 delta W is nothing but delta O2 delta net 1 into delta net 1 delta W. Delta O2 delta net 1 is nothing but product of the outputs of two neurons. Okay, O2 is the output of second neuron. O1 is the output of first neuron. So net 1 is the input to the first neuron. So we are taking derivative with respect to the input of another neuron. So the result is that the derivative is minus of the product of two outputs. And delta net 1 delta W is nothing but derivative of the net input with respect to the weight. So that naturally will be equal to the input arriving over that connection. So input arriving over that connection is the output of the hidden layer neuron. So I get delta O2 delta W as minus O2 into O1 into the input at the connection. I look at delta W1 delta weight. So delta W1 delta weight is delta W1 delta net 2 into delta net 2 delta W plus delta O1 delta net 1 into delta net 1 delta W. So here again, since O1 is a function of both net 2 and net 1, I have to introduce both these controlling variables and sum them up. And the chain rule is in the form of derivative of output with respect to net input and derivative of net input with respect to the weight. Now net 2 is not a function of the weight of interest. So delta net 2 delta W gives me 0 like before. Now I have derivative of output with respect to its own input, which is output into 1 minus output into into input arriving at the source side. So I have delta O1 delta W is equal to O1 into 1 minus O1 into H21. So what am I arriving at? I'm arriving at this expression for delta E delta W as summation of these two quantities, okay, multiplied by appropriate quantities. So delta E delta W 21 is this quantity minus T2 by O2 delta O2 delta W minus T1 by O1 delta O1 delta W. Now delta E delta W to 1 has been found to be minus O2 into O1 H21. Now when I multiply these by minus T1 by O minus T2 by O2, O2 and O2 will cancel. So I get minus T2 O1 H21. Minus and minus also will cancel. And here delta O1 delta W is O1 into 1 minus O1 into H21. So T1, O1 and O1 will cancel here. So I get T2 O1 H21 minus T1 1 minus O1 H21. Now 1 minus O1 is nothing but O2 because O1 plus O2 is equal to 1. So T2 O1 H21 minus T1 O2 H21. This is difference of the cross products. So it will give me minus T1 minus O1 H21. So the change in weight will be equal to this minus and minus will cancel, eta into T1 minus O1 into H21. Okay. So when I use softmax and use cross entropy loss, then the weight change expression for the outermost neuron is learning rate into difference of target and observed into the input arriving at the connection. Okay, so one more time, the change in weight for the connection is learning rate into difference of target and observed into the input arriving at the connection. Okay, and though we are showing it for only 2 neurons, this is a general rule which applies to all dense networks for the connection going to the softmax layer. For the connection going to the softmax layer, the change in weight is learning rate into difference of target and output, or target and observed, and input arriving at the connection. And how did we derive it? We derived it through the pure application um, uh, of partial derivatives and chain rule of partial derivatives and the summation rule of partial derivatives. Let me repeat: partial derivative, chain rule of partial derivative, and summation of partial derivatives. Now we can carry this forward, the same idea, again doing it from first principles. Whatever the weight change for hidden layer. Now hidden layer, the handicap is that we do not know the target values. So, but we have our mathematical machinery at our disposal. So change in weight, this red weight, which is W2111, weight going from hidden layer neuron number 1, first layer, to hidden layer neuron number 2, second layer, H21, to layer number 1, index number. So H21, H11, we are interested in the change in weight for this connection. So delta W2111 is minus eta delta E delta weight. I will again use the term weight to avoid cluttering of notation, of speaking out the notation. So by gradient descent rule, change in weight equal to minus eta into gradient of error with respect to the weight of interest. Now delta E delta W2111. E is a function of O2 and O1. So I have to bring in that loss expression. So I get delta E delta W equal to minus T2 by O2 delta weight minus T1 by O1 delta O1 delta weight. O1 and O2 are the constants. Now you see, we are interested in this weight change rule. This weight is quite far from the output values, and the weight influences the activation of H21. The activation of H21 influences net inputs in the outermost layer, and these net inputs influence O1 and O2. O1 and O2 in turn influence error. So all these influences have to be noted and kept in record. Now we are again armed with partial derivatives, chain rule of partial derivatives, summation of partial derivatives. These are mathematical machinery. So we can apply it. Delta E delta W equal to is a function of delta O2 delta W delta O1 delta W. Now a delta O2 delta W. Delta O2 delta W is delta O2 delta net 2 into delta net 2 delta W plus delta O2 delta net 1 into delta net 1 delta W. What is happening here? O2 is a function of both net 1 and net 2. Okay, so we have to introduce both these controlling variables. So delta O2 delta W is delta O2 delta net 2 delta W plus delta O2 delta net 1 delta W. Now, if it was not softmax, we will not bring in net 1. We will be happy only with O2 and net 2. Because it is softmax, we have to bring in net 1 also. Now, delta O2 delta net 2 is O2 into 1 minus O2, own derivative with respect to own input. And delta net 2 delta W2111 cannot be made 0 now. Earlier, you would have noted that derivative of net 2 with respect to the weight was becoming 0 because that weight was not influencing net 2 at all. Now, the weight influences both net 2 and net 1. So delta net 2 delta W I have to bring in. And delta net 2 delta O2 delta net 1 is minus O2 into O1. Okay, product of two different outputs. And delta net 1 delta W. Now net 2, what is net 2 a function of? Net 2 is a function of both the outputs from both the hidden layer neurons. So it's a function of H22 and H21. Okay, and net 1 is also a function of H22 and H21. So let's see delta O1 delta W. Delta O1 delta W is delta O1 delta net 2 into delta net 2 delta W plus delta O1 delta net 1 delta net 1 delta W. So I get again delta O1 delta net 2 as minus O2 into O1 delta net 2 delta W plus own derivative O1 into 1 minus O1 delta net 1 delta W. So the two terms in the derivative of error are taken care of now. I have found expressions for delta O2 delta W and delta O1 delta W. These are in terms of derivatives of the net input, net 1 and net 2. So I have more work to do. This more work is in the following form. Delta net 1, delta W211. Look at the picture. Okay, it is helpful to understand backpropagation through pictures when we have the network in our view. Net 1 is a function of H22 and H21, and W2111 influences both H22 and H21. So apply partial derivative. Delta net 1 delta W211 delta W is delta net 1 delta H21 delta H21 delta W plus delta net 1 delta H22 delta H22 delta W. Okay. Now we can see that W2111 influences only H21. H22 is not directly influenced by W, the weight of interest. So this can be neglected and this will be 0. So I get delta net 1 delta W as the weight value into delta H21 into delta W2111. So delta net 1 H21 is nothing but delta delta net 1 H21 is this net input and derived with respect to output of the hidden layer neuron. So this will give me the weight value here, only the weight value, because the net is weighted sum of the inputs. So delta net 1 delta H21 will be nothing but this weight. Okay, and delta H21 delta W2111, this H delta A derivative of the output with respect to the weight. Okay, derivative of the output with respect to the weight. So here I can apply chain rule again. Delta H21 delta weight is delta H21 delta net 21 into delta net 1 delta weight. And this chain rule application, what it does is that it brings in the input to the neuron into the picture, because we were only taking the derivative with respect to the output of the output with respect to the weight. I have to now bring in the controlling variable, which is the net input. Okay, so delta H21 delta net 21 will give me the derivative of the input output function. The input output function is the ReLU function. And delta net 21 delta W211 will be nothing but the input arriving at this connection. Okay, so we have come to this this stage now, that the backpropagating weight has come into picture. The weight coming back, weight connecting the output layer neuron to the neuron of interest, and this weight also going from O2 to the neuron of interest. Okay, so proceeding this way, we also get delta net 2 delta W2111. That is this net 2 and this weight value. We get again the backpropagating weight multiplied by the delta H2 delta W211, which is found to be equal to derivative of the ReLU into the input arriving at the connection. Okay, so when we take all these things together, we find that delta E delta W211, which is a function of the target output of both the neurons, can be finally looked upon as minus O2 O1 into backpropagating weight into derivative at the neuron of interest into input arriving over the connection. Okay, and derivative of the outermost neuron again, backpropagating weight, derivative of ReLU, and input are arriving on the connection. Now this O2 will cancel with the denominator O2, O1 will cancel with denominator O1, and now if we do the algebra again, I get delta E delta W is equal to T2 into 1 minus O2 into backpropagating weight into derivative of the ReLU into the input arriving at the connection minus T2 into O1 backpropagating weight derivative of the ReLU into the input arriving over the connection and a similar term. Okay, so by doing all these algebraic operation, we finally get the expression that the derivative of the loss function with respect to the weight is T2 minus O2 into W221 plus T1 minus O1 W121 into derivative of the ReLU into input arriving over the connection. So that's quite neat if you keep the diagram in view. The change in weight of this value, okay, change in weight of this value is learning rate into the difference in target and observed backpropagated over this connection. Difference of target and observed backpropagated over this connection. Okay, multiplied by these weight values, the weight value, the connections which are backpropagating this difference. Okay, and sum this up and take the derivative of the input-output function at the neuron of interest. The neuron of interest is the hidden layer neuron. And the connection is going from the lower layer into this hidden layer neuron. So the input coming to this connection, derivative at this neuron multiplied by a backpropagated quantity. That backpropagated quantity is difference of target and observed multiplied by the weight of the backward connection and summed with a similar quantity for the other neuron. Okay, so this is for the penultimate hidden layer. Okay, for the hidden layer below, the same delta will be backpropagated over the weights and summed up over all the neurons which are feeding back into the neuron of interest. Okay, so we have a neat expression. The neat expression is the change in weight is equal to eta into difference of target and observed multiplied by the input for outermost neurons. And for hidden layer neurons, it is learning rate into backpropagated delta into derivative at the neuron into input arriving over the connection. Okay, now it is the derivative r dash h21 or derivative of sigmoid which is the culprit for vanishing or exploding gradient. Okay, as we go down the layers, these gradients get multiplied and they become smaller and smaller because for sigmoid, the maximum value of the derivative is 0.25. But if we use ReLU, whose derivative is either 0 or 1, either the backpropagated delta remains same or it becomes 0 completely. There is no progressive attenuation. Okay, but that's a different matter. I think I'll close here just by repeating the fact that we did nothing more sophisticated than just making use of partial derivative very cleverly. Okay, and whenever we are interested in a quantity, we find out this quantity, this parameter, which are the variables in the network which are influenced by this parameter. This parameter influences the input to the neuron H21, which influences the output going from H21. That output influences all the net inputs going to the next layer. All those net inputs influence the outputs in that layer, and that output influences the error function. So if this is the chain of influence, then the chain of error will follow only the backward path. Okay, the forward path was input, output influencing these two inputs influencing output again. The backward path will be error coming back by the same path to the neuron, where it is getting multiplied by the derivative of the input-output function, and the input over the connection is also input. Okay, so let me stop here and sort of urge you to look at the mathematics here, which is no more sophisticated than partial derivatives, chain rule of derivatives, and summation of partial derivatives. Okay, so are there any questions? On the chat, there was a question. So Vishal, am I audible?
Yes, sir.
Vishal had asked, can LSTM or CNN with self-attention capture long-distance relationships in sentences? So LSTM or CNN with self-attention. CNN with self-attention, how will the architecture be? I need to think. But LSTM with self-attention is really the transformer. And the transformer is supposed to capture the long-distance relationship, yes.
So CNN, when it is used to like do a sequence-to-sequence model, so while while the decoding part, I am using self-attention. Well, for each word, I'm assigning a self-attention parameter. So in that way, can it be used to capture long-distance relationship?
Okay, so in self-attention, what will happen is that we'll have to build a block where the encoder output, the encoder output for that particular token. Let's understand self-attention first. The encoder output is actually tapped, right? In the sequence, the encoder output is tapped. Instead of converting the whole encoder sequence to one single vector, we tap the output at every stage of the token. And that token is connected to all other tokens in the sequence. And the weights for these token-to-token connections are learned, right? So that is the main point about the self-attention.
Yes,
Okay?
sir.
So this is the main mechanism. Now, what you're saying is that have a CNN. CNN, first of all, is not a sequential processing machine, not over the whole sequence. So have the CNN and have the vectors of the words, okay? So then I have the matrix in the form of words in the rows and the vectors components in the column. And then a kernel goes over this whole matrix, okay? Capturing n-gram information in the form of n-way filters. So this is how it works. Now, what will be attention for CNN? Attention by definition is comparing one token, the token number I, with all other tokens in the sequence by definition. Okay. So now for a CNN, getting a self-attention to my mind is redundant, isn't it? Because you are already using the pooling and filtering. So comparing every word with every other word, I don't know, maybe useful, but I have not seen such an architecture.
So CNN generally works in a certain window, like bounded window. So if we use a self-attention and get the parameters from outside the window, then we are getting long-range dependency.
I see, I see. Let me think about it. And have you seen such architecture?
Yes, on neural story generation that they're using, but I'm not exactly understanding how they're using it. Like, I asked it.
Okay. So I think in one of the classes, I'll also discuss attention in detail, going from first principles.
Yes, sir.
Okay. And then can you explain the weight convention? I did. Are we wasting lots of energy training huge GPT-like models just to rote learn the entire web? I think you are right. So in GPT or these kind of large-scale transformers, we are learning billions of parameters. And it is a principle, you may call it a philosophical principle. We have to, do a lot of beating around the bush, हाथ पैर मारना जिसको बोलते हैं पानी में उतर के. Okay, you have to try many things and keep many hypotheses open in the search space if we do not have knowledge. So if you're not exploiting the geometry in the image or any kind of special properties of the image, or if you are not using the linguistic properties of the sentence, namely noun, verb, adjective, etc., or their semantic properties, then we have to perforce learn many parameters which are corresponding to the raw input. Okay, because there is no specialized knowledge used, linguistic knowledge used, we have to make use of many parameters. So I think the presence of very large number of parameters is due to lack of understanding and knowledge for the particular problem situation. It has its own pros and cons. We become independent of any situation specific constraints, but at the same time we have to waste resources because of lack of knowledge. And of course, training of such networks is extremely energy consuming. Okay, so that's it. So I think we will now stop here and we'll meet for information extraction work update after 5 minutes. Thank you.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you.
sir.